In this video, I hope to present the correct solutions to the 2019 free response questions for the AP Physics 1 exam. The solutions that I'm providing are without a proper rubric for these questions, and they don't come at all from the College Board. It's just me trying to disseminate the solutions that I can provide as best as I can. If you feel that I've made a mistake anywhere, please make sure to let me know. But I'm going to go ahead and go through all 5 questions, and we'll see if I can't provide a correct solution to each question. Starting with question number 1, this was a 7.13-minute question. The question reads, identical blocks 1 and 2 are placed on a horizontal surface at points A and E respectively as shown. The surface is frictionless except for the region between points C and D where the surface is rough. Beginning at time TA, block 1 is pushed with a constant horizontal force from point A to point B by a mechanical plunger. Upon reaching point B, block 1 loses contact with the plunger and continues moving to the right along the horizontal surface toward block 2. Block 1 collides with and sticks to block 2 at point E, after which the two-block system continues moving across the surface, eventually passing point F. And for part A, we are asked to, on the axes below, sketch the speed of the center of mass of the two-block system as a function of time from TA until the blocks pass point F at time TF. The times at which block 1 reaches points A through F are indicated on the time axis. So this is a graph of the center of mass of the two-block system as a function of time. Initially, I know that both blocks are at rest. So the center of mass has a speed of 0 starting off at time TA. And while the center of mass of the two-block system, the speed of the center of mass of the two-block system depends on the movement of either block. Block 2 doesn't move at all until we get towards the end of the graph. And so I can essentially graph the speed of the center of mass and the changes in the speeds of the center of mass by just looking at block 1 for most of this graph. I know that between times TA and TB, the force from the plunger is going to be pushing forward on block 1, and that force from the plunger is going to provide a constant force, which is going to cause a constant acceleration. Since the vertical axis isn't labeled at all, I should just go up somewhere. Maybe I'll go to this point here to indicate that there is a positive acceleration from that positive net force going to the right-hand side. So the speed is increasing from the plunger. And when it gets to point B, it loses contact with the plunger, and between points B and C is a frictionless surface. So now the block 1 is moving, but it should move at a fairly constant speed from point B to point C. And so in my graph, I'm going to make that a horizontal line going from point B to point C. As the block arrives at point C, there's a surface there with some friction, and that frictional force is going to point to the left, and it's going to slow that block down a little bit. And so the block 1 is going to experience a negative acceleration. So the slope of my graph should be negative. I know that after it gets through this segment CD, it still is going to hit block 2. So the thing doesn't slow all the way down to 0. It just needs to slow down a little bit. And so maybe my graph looks something like this. Between C and D, it slows down with a constant force due to that constant amount of friction that was present in that segment. From points D to E, there is another frictionless surface, and so maybe we should have another flat region where the speed is constant. And the reason why the speed is constant in segment DE is the same as why it's constant in segment BC, because while the surface is frictionless, the net force on the block 1 will be 0. The hardest part of this graph is the last part. Everybody knows that when block 1 collides with block 2, the mass of the stuff that's moving is going to increase, and therefore the velocity of the stuff that's moving is going to decrease. And maybe you can imagine writing a conservation of momentum equation, which looks something like Pi equals Pf, where the mass of the first block times the velocity of the first block equals the sum of the two blocks' masses times that final speed v2, maybe we'll call it. And you've certainly learned that the increase in the mass here is going to cause the speed to decrease. But the graph that we've been making is for the center of mass of the two-block system. The center of mass of the system cannot change unless there is an external force to speed up or slow down the blocks. Since both blocks 1 and block 2 are in the system that I'm graphing the center of mass of, the speed of the center of mass of, then the speed of the center of mass does not change when one block collides with the other. And the reason why the center of mass, the speed of the center of mass of this two-block system is not changing is because when block 1 collides with block 2, the amount that block 2 speeds up will be equal and opposite to the amount that block 1 slows down. And so for that reason, confusingly, the speed of the center of mass should be constant as block 1 collides with block 2. And so my speed should be constant up until TF. If they only ask me to plot the speed of block 1, then the first 4 segments of my graph would be the same. And after those first 4 segments are done, we should expect that the speed drops off to about half the value, because the mass doubled, so the speed would go down by half. But I think for full points, we would want to draw the red line that I've drawn. Part B, which is the last part of question number 1, reads, the plunger is returned to its original position and both blocks are removed. A uniform solid sphere is placed at point A as shown. The sphere is pushed by the plunger from point A to point B with a constant horizontal force that is directed toward the sphere's center of mass. The sphere loses contact with the plunger at point B and continues moving across the horizontal surface toward point E. In which intervals, if any, does the sphere's angular momentum about its center of mass change? Check all that apply. My first thought when I'm thinking about the angular momentum of something changing, a change in angular momentum, I know that this has to be due to some external torque that is being applied to the sphere. And I also know that since angular momentum is equal to the angular momentum of this sphere is equal to the sphere's moment of inertia times its angular speed, that since the moment of inertia of the sphere is constant, the only way that the angular momentum is going to go up or down is if the angular speed goes up or down. And that's going to be due to that external torque. And so let's look at a picture of the sphere and the forces that are exerted on the sphere. At the contact point between the surface or the table and the sphere, there's a normal force that passes straight through the axis of rotation. And so that normal force is not capable of causing a torque on the sphere. And so it will not rotate due to the sphere, due to the normal force. The gravitational force is a force that is exerted on the sphere's center of mass that points downward. And for that reason, the gravitational force cannot cause the sphere to rotate either. The force from the plunger is applied to, as it says in the problem, toward the sphere's center of mass. And for that reason, that applied force can also not cause the sphere to rotate. And so I think that for segments AB and BC, it's not possible for that sphere to rotate because there's not a force that is ever acted on the sphere that would allow rotation to occur. None of these forces can cause torques because they all are either acting through, pointing toward, or originating from the center of this object. However, in segment CD, there's going to be a frictional force that's applied at the contact point between the two surfaces. And that frictional force is going to oppose the rotation, or it's going to oppose the motion of the object, right? So at the contact point there's going to be a frictional force that is exerted, and because that frictional force is exerted a certain distance away from the axis of rotation, that would be like the radius of the sphere, then the frictional force is capable of exerting a torque on the sphere, allowing it to rotate. And so I think that in segment CD, that frictional force is going to exert a torque on the sphere and cause it to rotate. And if it starts rotating, as I showed above, the angular speed will increase, therefore changing the angular momentum. Lastly, in segment DE, I think that once that frictional torque goes away, the ball can't rotate any faster, or it can't rotate anymore. However, because the surface is frictionless and it already was rotating, I think that the sphere will continue to rotate even through segments D and E, and I don't think that that rotation will slow down at all, because I don't think that there's anything present in segment DE that will allow for the energy that was in the rotation of the sphere to go away. So for that reason, my explanation here would be some indication that the frictional force on the sphere causes a torque that makes the sphere rotate. And this is a briefly explain your reasoning question. So maybe I could have come up with a better explanation or a better way of saying that, or maybe somehow tie it to the angular momentum a little bit better. But in general, I think that the reasoning is there. So that's the end of the first problem. Problem number 2 is a 12-point problem. That's a 25-minute problem, which says this problem explores how the relative masses of two different blocks affect the acceleration of the blocks. Block A of mass MA rests on a horizontal tabletop. There's negligible friction between block A and the tabletop. Block B of mass MB hangs from a light string that runs over a pulley and attaches to block A as shown above. The pulley has negligible mass and spins with negligible friction about its axle. The blocks are released from rest. Part A1 says, suppose the mass of block A is much greater than the mass of block B. Estimate the magnitude of the acceleration of the blocks after release. And so for the first part here, A1, we're to assume that the mass of block A is much greater than the mass of block B. And so I'm thinking that despite the mass of block A being much greater than the mass of block B, I think the system will still accelerate. And the reason why I think it's still going to accelerate is because the table is frictionless, or at least has negligible friction. And so for that reason, any force applied to block A will cause it to move to the right. And so the mass of block B, despite being much smaller, is going to cause a tension in this rope, which is going to pull block A to the right. And even though block A is very heavy, or at least has a mass much greater than block B, that horizontal force is going to cause block A to move to the right. However, because the mass of block A is much greater than the mass of block B, I think that this acceleration will be very small. And so I'm not sure exactly what to write for A1, but my estimate of the magnitude of the acceleration might be something like very small, but not 0. Depending on how the rubric looks for this question, you might be able to say approximately 0 or things like less than g, but I'm not sure exactly what they're looking for there. Briefly explain your reasoning without deriving or using equations. So if I used Newton's second law to write an equation here, I could probably come up with pretty good reasoning to support why the acceleration would be small but not 0. But I think just this idea that the table is frictionless and block B exerts a horizontal force on block A, then maybe that's sufficient enough to convince somebody that the system's going to accelerate, but as they stated in the problem, since block A is much heavier, then the acceleration is not very fast. For part 2, the assumption now is supposed to be that the mass of block A is much less than the mass of block B. And with this assumption, then block B is going to want to fall down when it's released. And block A is the thing that kind of is supposed to be holding it up, right? And so if the mass of A is much, much less than the mass of B, then what that means is block B should fall with a fairly close acceleration to it being in free fall, which would just be the acceleration due to gravity. And so my answer to A2 might sound something like approximately g, or about 9.8 meters per second squared, or maybe something like slightly less than 9.8 meters per second squared, something like that. And briefly explain why I think my answer there is, the mass of block A is not equal to 0. I'd probably write this a little bit more professionally, but the mass of block A is not equal to 0. Therefore, block B can't be in free fall. But since block A is much less than block B, it's going to be pretty close to free fall. Now, this next part is going to ask us to look at the free body diagrams of block A and B. Now, suppose neither block's mass is much greater than the other, but that they're not necessarily equal. Okay, so what that means is there's still the chance that they would accelerate, right? Because block B is going to pull down on block A, and maybe they're accelerating, and they want us to say, on each dot, draw and label the forces, not components, exerted on each block after they're released. Represent each force by a distinct arrow starting on and pointing away from the dot. So these are the standard directions for the free body diagrams for AP Physics 1. All right, so on block A, there's going to be a normal force that points up from the table. There's going to be the weight of block A pointing down, and that could be written as ma times g. And then there's going to be the tension force that's pulling on it to the right. That tension force also pulls up on block B, and the weight of block B is mbg and points downward. So I think that that's a pretty good, couple of free body diagrams for those blocks. Perhaps I should have shown more clearly that the weight of block B pointing downward is probably greater than the tension pointing upwards because the system is accelerating to the right and downwards. Other than that, I think we've got all the forces on there. Question number 2 has parts C, D, and E as well. So this was a longer question. It was a 12.25 minute question. In part C, says to derive an equation for the acceleration of the blocks after released in terms of ma, mb, and physical constants as appropriate. Because this is a pulley, block, table equation, I know pretty quickly that I need to use Newton's second law to write an equation that relates the acceleration and the net force. And I also know that for this two-block system, that I can write one equation that wraps around this pulley. And so the way that I would typically think about this is I would draw in all of the forces that point along this direction, along the direction of this green arrow. And I'm going to write one Newton's second law equation for that. So any force that points in the direction of that green arrow, I'm going to call positive. And any force that opposes that green arrow, I'm going to call negative. Okay? So first, the tension on the tabletop is positive. It points along the direction of the green arrow. The next tension is negative. And the force after that, mbg, is positive. Since I wrote the forces acting in that direction on both boxes, then I'm going to write the sum of the masses for both boxes. So ma plus mb. And the acceleration that I write at the end of this Newton's second law equation would be the acceleration of the two-block system. And since I called the direction of the green arrow positive, then my acceleration is positive. So all I have to do for this equation is cross off the t's and solve for a. So I divide by the sum of the masses on both sides. This is mbg divided by ma plus mb. And so I believe that this is the equation that they wanted me to derive. Okay? And hopefully it meets the requirements. It's in terms of ma, mb, and physical constants as appropriate. And now we're moving on to part D. Okay, part D says consider the scenario from part A2 where the mass of block A is much less than the mass of block B. Is my equation consistent? So my reasoning there was that because the mass of block A was so much less, then the thing essentially falls in free fall. And the acceleration should be equal to g. In my equation that I just derived is A equals mbg divided by ma plus mb. And so let's think about the denominator of this equation. If the mass of A is much less than the mass of B, when I add A's mass to B, then that is an extremely small addition. And so for that reason, I mean, just think about what if B was like 10 kilograms, but A was, 0.1 kilograms. Those two numbers added up, and this number alone are about the same size. So for that reason, we can pretty much just ignore the mass of A in the denominator of that equation. And if you notice, once that goes away, mb is on top and bottom, and it would cancel, giving us an acceleration approximately equal to g. And so I would check that yes, my equation is consistent with my reasoning, and then I would provide a brief explanation that in the equation, because the two terms are additive on the denominator, then one going away means the masses will cancel and the acceleration will be approximately g. Part E says while the blocks are accelerating, the tension in the vertical point portion of the string is T1, and the pulley is replaced with a second pulley whose mass is not negligible. And then when they're released, they want to know whether the tension in that vertical portion of the string, so this portion of the string here, which is first T1, then becomes T2, whether it's going to be greater than, less than, or equal to. And my thought here is, let's write a Newton's second law equation for that block, that bottom block. I would get T minus mbg equals, and actually I think I just started using the opposite sign convention as what I used before. So let's just use the same sign convention. So that would be minus T plus mbg equals ma. And what I notice about this is if I solve this for t, I would get, if I add t to the right and then subtract ma to the left, I would get mbg minus ma for the tension. And I think that if I attach a pulley that's harder to rotate, its mass is not negligible, it's not easy for that pulley to rotate, I think that that is going to cause the acceleration of the system to go down. And if the acceleration of the system decreases, then in this equation I would be subtracting a smaller number, which means that the tension is increasing. So I think that when the pulley with the non-negligible mass is attached, I think that new tension T2 is going to be greater than T1. And my brief reasoning here is probably going to be that due to the energy required to rotate that pulley, that heavy pulley, the acceleration is going to be decreased and the tension will increase, which is in accordance with this Newton's second law equation that I wrote out. I think that is the end of question number 2. Question number 3 is a 12.25-minute question, and this is the experimental design question. We have a projectile launcher that consists of a spring with an attached plate, as shown in figure 1. When the spring is compressed, the plate can be held in place by a pin at any of the 3 positions A, B, or C. For example, figure 2 shows a steel sphere placed against the plate, which is held in place by a pin at position C. The sphere is launched upon release of the pin. A student hypothesizes that the spring constant of the spring in the launcher is the same for different values of the compression distance. So, regardless of where I, compress it to, the spring constant will be the same. That's a hypothesis. So state a basic physics principle or law the student could use to design an experiment to test the hypothesis. Because I'm compressing a spring, the thing that jumps to my mind immediately is the conservation of energy. Right? I could do an experiment where the spring gets compressed, launches the ball to a certain height, and that the energy stored in the spring would be conserved, and I can measure the height and maybe measure something about the compression distance of the spring in order to see if energy is conserved. And I could see if that spring constant was the same in these different trials for different compression distances. So part A2 says to use the principle or law to determine an expression for the spring constant. If I compress the spring, then some energy will get stored in it, equal to 1/2 kx squared, where x is the compression distance of the spring. And if I let go of that spring, and maybe I turn the spring to be vertical, then it's going to launch that ball straight up into the air, and all of the energy from the spring will get converted into gravitational potential energy. So we have an equation that says spring potential energy will get converted into gravitational potential energy. And for this reason, I should be able to solve this for the spring constant, which I believe will be 2 mgh divided by x squared. And so here's an equation where if I could measure the height, the mass, and the compression distance, I would be able to tell you what the spring constant was. And I think that all of those things could be easily measured in a high school physics lab, and so I think that that fits the bill for part A2. Now we're asked to design an experimental procedure to test the hypothesis in which the student uses the launcher to launch the sphere. Assume equipment usually found in a high school physics laboratory is available. So the first quantity that I'm going to measure is the mass. The symbol for the quantity is m. And the equipment to measure it, maybe I just use a spring scale for the mass, or that measures the mass. The second quantity I want to measure is the height. The symbol that represents that in my equation is h, and for that maybe I just use a meter stick. The third quantity I need to measure is the compression distance. The symbol for that is x. And I could just use, another meter stick to measure that, but maybe more reasonably, something just like a ruler to measure that smaller distance for the compression. And I think that those are the only three things that I need to measure in order to determine the spring constant. Question number 3 has more to part B and then also parts C and D. Part B says, describe the overall procedure to be used to test the hypothesis that the spring constant of the spring inside the launcher has the same value for different compression distances, referring to the table. Provide enough details so that another student could replicate the experiment. Include any steps necessary to reduce experimental uncertainty. As needed, use a symbol defined in the table and/or include a simple diagram of the setup. So I'm not going to write all of this out, but I think I would take the launcher and I would set it vertical. I would put the sphere in there at these different compression distances. I would measure those compression distances. I would shoot the ball up. And then I would probably have to record a video or just have a couple people watching it to be very careful about how I'm going to measure this maximum height that is achieved by this. And so I'm going to make sure that I'm going to do this in several trials. I'm going to make sure that I hit all these compression distances, and I'm going to be very clear about measuring the mass of the ball before I do any of this. And then I'm probably going to say, since that height is difficult to measure, that I'm probably going to do each compression distance 2 or 3 times and then average the height results that I get for each trial. And I think that that would be enough for somebody to be able to collect the data that could be used to measure whether or not that spring constant was in fact constant. Part C says to describe the experimental data, how the experimental data could be analyzed to confirm or disconfirm the hypothesis that the spring constant was constant for different compression distances. Referring back to my previous equation, I think we wrote a 1/2 kx squared equals mgh conservation of energy equation, in which case we got that the spring constant was equal to 2 mgh divided by x squared. In order to analyze this data, what I'd really like to do is have a graph where the slope of the graph represented the spring constant, and then if the slope of the graph was constant, I would be able to say that the spring constant was also constant. So what I'd like to do is match up the equation that I have to the equation y equals mx plus b, where the slope is represented by the spring constant. And perhaps the easiest way to do this would be to first multiply both sides by x squared. So now we're back with an equation that looks like this. And then I'm going to divide both sides by 2mg. And so what I would have here is h on one side and x squared times k divided by 2mg on the other side. And now I'm going to take this equation in yellow and I'm going to flip it. H equals x squared times k divided by 2mg. So I want to point out just a couple things about this equation. I'm going to write it one more time on the left-hand side, and I'm just going to flip the way that I'm writing the things on the right-hand side of the equation. So I'm going to write it as h equals k divided by 2mg times x squared. And now I want to compare this to y equals mx plus b. First, I notice that in the equation I have in blue, there's no plus anything, plus 0. So the y-intercept should be 0. Secondly, if I make a graph of height versus x squared, then the slope of that graph should be equal to k divided by 2mg. And k is supposed to be a constant, m is certainly a constant, and g is a constant. So the only thing that could vary in the slope is the spring constant, depending on whether the student's hypothesis is correct or not. And so if I made a graph of h versus x squared, plotting h on the y-axis and x squared on the x-axis, then if the student's hypothesis is correct, we should get a straight line that has a slope of k divided by 2mg. And if the student's not correct, then the slope of this graph is probably going to do something like this or something like this. And so it says to describe how the data could be analyzed. I'm not going to write out all these equations probably, but I will probably just write out the equation that I got, show how it matches up with y equals mx plus b, and then tell them to make a graph of h versus x squared and check to see whether or not the slope of the graph is linear. The last part, part D, says another student uses the launcher to consecutively launch several spheres that can have the same diameter but different masses, one after another. Each sphere is launched from position A. Consider each sphere's launch speed, which is the speed of the sphere the instant it loses contact with the plate. On the axes below, sketch a graph of launch speed as a function of sphere mass. So now I could modify my conservation of energy equation to say that the elastic potential energy that is stored in the spring gets converted not into gravitational potential energy, but into the initial kinetic energy that the ball has as it leaves the launcher, 1/2 mv squared. Right, where v is that launch speed that they want me to plot in the graph. So they want me to make a graph of v versus m. And in this conservation of energy equation, I have a v and an m, so I should be able to compare them. First, I'll cancel the 1/2, and then I want to solve this for v. And so when I solve this for v, I'm going to divide both sides by m, and then I'm going to square root both sides of the equation. And this will leave me with an equation that says v is equal to the square root of kx squared over m. And so I know that v is proportional to 1 over the square root of m. So as the mass increases, the velocity will decrease, and so the relationship is definitely inverse, but it's also square root dependence. So I think we can comfortably just make a graph that looks something like this, where it's a 1 over relationship. It's hard to know whether a student has shown the square root dependence or not in the equation, but definitely as the sphere mass increases, the launch speed should decrease, and it should be a square root kind of relationship like that. I believe that that is the end of problem number 3, which means there's 2 problems left. Number 4 says a motor is a device that, when connected to a battery, converts electrical energy into mechanical energy. The motor shown above is used to lift a block of mass m at a constant speed from the ground to a height h above the ground in a time interval delta t. The motor has constant resistance and is connected in series with a resistor of resistance R1 in a battery. Mechanical power, the rate at which mechanical work is done on the block, increases if the potential difference voltage drop between the 2 terminals of the motor increases. The first part asks me to determine an expression for the mechanical power in terms of mh and delta t. When I think of power, I think of 2 equations, I delta v and delta E over delta t. And I think since m, h, and delta t need to be in the equation, it makes a lot more sense to use the bottom equation to derive this expression. And I know that while the power that the motor has is coming from the circuit, we can express that power in terms of its ability to raise that block. And for the block, the change in energy is equal to its change in gravitational potential energy, which is just equal to mgh. Therefore, my expression for the power is just going to be mgh divided by the time it takes to lift it up, delta t. Now for part B, it says, without m or h being changed, the time interval delta t can be decreased by adding one resistor of resistance R2, where R2 is greater than R1. How should the resistor be attached? I think that the answer that makes the most sense here is to attach the resistor in parallel with R1. However, I think there actually might be a couple of answers that will work here. For instance, if I attach the new resistor in parallel with R1, something like this, so R2 is there, then I know that the value of R1, which is some number, is going to be less than the equivalent resistance of R1 and R2. So if you, for any value of R1 and R2, if you found the equivalent resistance, Rp, that's always going to be less than R1. And by Ohm's law, which is V equals I times R, if the equivalent resistance decreases, then the current will increase for a constant voltage of the battery. And so by decreasing the equivalent resistance of this circuit, I believe that the current coming out of that battery is going to get bigger. And if the current coming out of that battery is going to be bigger, then the voltage drop across the motor will be bigger. They said that this motor has a constant resistance. And so this resistance is constant. And I have now engineered a way to get a greater current out of the battery, which means that the potential difference across that battery will increase. Or sorry, not across the battery, but across the terminals of the motor. Therefore, that greater power being delivered to the motor should decrease the amount of time it takes to lift up the block. And so all you would have to do in this paragraph is to try to figure out how to take everything that I just said and apply it to the situation in the form of words, with maybe the help of a little diagram or so, or a couple of equations. And I think I would just say that in general, adding the resistor in parallel reduces the equivalent resistance. That reduced resistance increases the current, and the increased current delivered to the motor will cause there to be a bigger voltage drop across the terminals of the motor, which will increase the mechanical power. That increase in mechanical power corresponds to a decreased amount of time to lift up the block. The last question is a 7.13-minute question, and it's about waves. It says a tuning fork vibrating at 512 Hz is held near one end of a tube of length L that is open at both ends. The column of air in the tube resonates at its fundamental frequency. The speed of sound in air is 340 meters per second. The first part asks me to calculate the length of the tube. And in order to do that, I need to know a little bit about what the wave looks like in the tube. You should remember that at an open end of a tube, there has to be an antinode, right? So there's not a node, there's an antinode at both ends of the tube. And the fundamental frequency would be the first harmonic, the biggest wave that we can fit inside of this tube. And so there's only going to be one node which is in the middle of this pipe. And so the standing wave will look something like that. And what I observe about this is I see 1/4 of a wavelength on the left-hand side and 1/4 of a wavelength on the right-hand side. Anytime I go from equilibrium up to a maximum, that is 1/4 of a wavelength. And so I see 2/4 of a wavelength inside of that pipe. So overall, I see 1/2 of the total wavelength inside the pipe. And if the pipe has a length L, then the true wavelength needs to be twice as big as the pipe. So the true wavelength is twice as big as the pipe. And by my wave equation, which says V equals F lambda, if the wavelength is twice as big as the pipe, I should be able to solve for L quite easily in part A. So L is equal to V divided by 2F. The speed was given to me as 340 meters per second, and the frequency was 512 hertz. And I think that that comes out to be something like 0.33 meters for the tube, which at least is a reasonable number for the length of a tube. Part B says the column of air in the tube is still resonating at its fundamental frequency. On the axes below, sketch a graph of the maximum speed of the air molecules as they oscillate in the tube as a function of position x from x equals 0 to x equals L. So we're essentially plotting the speed as a function of position along the length of the tube. And what I know about nodes and antinodes is that at the location of a node, the air is not moving at all, and at the location of an antinode, the air is moving back and forth very rapidly. And so for that reason, I'm looking up at my picture of the wave above, and I notice that in the middle of the pipe at L over 2, there's a node, and so there should be 0 speed. And at either end of the tube, there's an antinode, and that antinode should correspond to some maximum speed. And lastly, since we know that the shape of the wave inside of that pipe is sinusoidal, then we should expect the relationship between the speed and the position to also be sinusoidal. So I'm assuming that the graph should look something like this. Okay, so that's the speed as a function of position, basically getting at whether you know how the air moves at nodes and antinodes for a standing wave. The next part of this problem says the right end of the tube is now capped shut, and the tube is placed in a chamber that is filled with another gas in which the speed of sound is 1005 meters per second. We're to calculate the new fundamental frequency of the tube. So if the right end of the tube is now capped shut, the pipe will look something like this. It'll be open on the left, but it'll be closed off on the right-hand side. And so now there will be a node at that closed end, but there will still be an antinode at the other end. And so there's a fundamental difference between open-closed and open-open pipes. And that is here, the biggest wave I can fit in only has 1/4 of the wavelength. Right? For the first case, where it was an open-open pipe, we saw that 1/2 of a wavelength fit inside the tube, and now only a 1/4 wavelength fits inside. So now the expression for the wavelength should be that lambda is equal to 4 times the length of the pipe. 4 times bigger than what I see there inside the pipe for the fundamental frequency when it's open-close. So for that reason, I'm going to rewrite my equation, V equals F lambda, except now I'm going to write 4L for the wavelength. And they're asking me to solve for the new fundamental frequency, so F is equal to V divided by 4L. The new speed of sound is 1005. 4 is there. And the length is going to be the same length of the pipe as what I found up above. So that 0.33 number needs to be used there. And I think that when we solve for the frequency here, we get something like around 700 hertz. And so the new fundamental frequency is going to be on the order of about 700 hertz. I don't know exactly what that number is going to be. And so I think that that takes us through the 5 free response questions. If I've made any mistakes, please let me know. But hopefully the answers to these questions were pretty well represented.